Beijing Center for Pesticides Alternatives. So please help me to welcome Conny in this.
Thank you, Martha. Thank you for having me. I'd like to talk about the Balance Act, the crucial role of microbiome on the antimicrobial free fat piglets. I'm Conny Turni. Some of the data is from Lenny, so I'd like to thank him for that. I will talk about why is gut microbiota so important, when does gut microbiota establish, what bacterial phyla and families are important in the microbiome, what products are produced by the microbiome, and then a conclusion. Now, the gastrointestinal tract consists of trillions of bacteria belonging to more than 1,000 taxonomic groups. Some of them are not even cultured or identified. The microbiome is influenced by host factors, management and environment, and the diet and additives. When the microbiome is in balance, there's normal behavior, positive immune response, healthy gut structure and function, normal central nervous system functions, good stress responses, excellent health status, and good performance. The microbial function is to protect the intestinal tract by direct competition with the host for limited nutrients, regulating host immune responses, increasing the resistance to pathogens and potential harmful bacteria colonizing in the intestine, and reconstructing the homeostasis of the intestine. Now let's have a look a little bit at this. So the immune system, the gut immune system contains 70 to 80% of the whole body's immune cells. So this has a profound effect on the development of the host immune response, including the development of the innate and the adaptive immune responses. Gut microbiota regulates and fine-tunes the immune system throughout the life of the pig. Resonant microbiota is recognized to suppress unnecessary inflammatory responses, thereby helping to maintain immune homeostasis. The antibody response, studies have shown that the antibody response is delayed in germ-free piglets due to the immature immune structures. Another interesting part is that there is a microbiota gut-brain axis. Explicitly includes the role of gut microbiota in the biochemical signaling events that take place between the gastrointestinal tract and the central nervous system. There's also an influence on the behavior. Apparently, in pigs, gut microbiota has a profound effect on the porcine appetite and feeding behavior. When the sow is fed a maternal Western diet during gestation and lactation, this has significant consequences for the piglet's blood lipid levels, microbiota activity, microbiota gut-brain axis, and neurocognitive abilities after weaning. However, we don't know to what extent and how is the animal behavior driven by the microbiome. Gut microbiota also plays a vital role in the process of stress responses. So nurturing an optimal gut microbiota may help to manage stressful situations and to increase the productivity. It has been long known that stress and the associated activity of the hypothalamus, pituitary, adrenaline axis can influence the gut microbial composition. The axis modulates cortisol and corticosterone secretion, which in turn regulates the immune circulating cytokine secretion in the gut, which can further influence intestinal barrier function and alter gut microbial composition through the microbiota gut-brain axis. In other species, it was found that stress changes the microbiota. Among these changes are a decrease in alpha diversity, upregulating of pathogen-related pathways. Stress also can lead to changes in the gut homeostasis and a weakened immune system. increases the risk for colonization by pathogenic bacteria. It has also a profound effect on the absorption of feed. Gut microbiota plays a crucial role in absorption and metabolism of feed, regulating gut motility and intestinal barrier homeostasis. So to have a balance between the beneficial and the harmful material in the gut, one should have at least 85% good bacteria and only 15% bad bacteria. And this is very important for the health and the productive performance. And disease is normally accomplished by an imbalance. What we call an imbalance is a dysbiosis. Dysbiosis can cause detrimental changes in the gut, affecting the digestion of ingested food, nutrient absorption, and mucosal barrier function, leading to translocation of infectious bacterial species and inflammatory response. This can affect feed conservation ratio, productivity, performance, and overall health. Now, what is the gut microbiome? Plays an important role in the 3 levels of the gut barrier. It's the integrity of the gut lining, it's the competition with pathogens, and it's the immune system modulation. Now, what bacteria are we normally encountering? So this is the phylums, and I have to say something here with the phylums. Researcher and taxonomy have unfortunately changed all the phylums. So when you read firmicutes, it's now Bacillolota. When you have bacteroides, it's Bacteroidota. And when you have Actobacteria, it's now Actinomycetota. And if you have Proteobacteria, which are normally the E. coli, that's now Pseudomonadota. So just to confuse us all, they always do that, unfortunately. So let's have a look a little bit more at this. So the dominance of some of these bacterial species is associated with the use of mono, di, and oligosaccharides. So in the phylum Bacteroidota, there is the Bacteroideaceae family. In the phylum Bacillota is the Clostridiaceae, the Lachnospiraceae, and the Lactobacilliaceae. In the phylum Pseudomonadota is the Enterobacteriaceae. They're all associated with monodi and oligosaccharides. So how is the microbiome established? Well, there was a belief, or is the belief still, that the newborn piglets, the microbiome is established rather soon after birth, when the piglets get seeded during the birth process from the environment, from the south vaginal canal, feces, udder, mouth, skin, and the colostrum during ferret. And then during lactation, it's a fecal transfer from the sow to the piglets. However, that might not be the case. So recently a study by Noland looked at piglets that were born prematurely, or stillborn I should say, and born alive, and some that had sucked. And the study showed clearly that the microbial colonization of the spiral colon had occurred in stillborn piglets. And this would suggest that the microbial exposure was actually prior to birth. They also found that alpha diversity indicated that the number of taxa and community richness were higher in piglets that sucked, and the community evenness was lower in stillborn than in comparison to born alive. Now the interesting fact too is that when we look here at the blue one, the light blue one, which are the Pseudomonadota, which are the E. coli, they are actually in high abundance there. And the other one is the orange one, which is Bacillota. So So there's a lot of E. coli coming in there. There is a concept of providing the right microbiome before birth. Is one of the ways to establish a good microbiome. So spraying the environment of the sow before farrowing or the piglet environment with good bacteria to start the piglets off with good bacteria is one of the beliefs. The concept of paying attention to the sow's nutrition pre-farrowing helps to improve the microbial profile, ensuring sows are fit for farrowing and piglets are exposed to a healthier microbiome profile. This in turn leads to increased vitality at and after birth. So during the lactation, the main bacteria are the fumigates, which are now called Bacillota, and the Bacteroidota. Bacteroidota are with 38.7% around there, and the Bacillota are 54%. Now, after weaning, this increases, there is Povitalaceae in the phylum Bacteroidata and Ruminococcoaceae in the phylum Bacillota. In the ileum, the Lactobacillus, Streptococcus, Clostridium become more abundant. Creep feed offered during lactation can facilitate a smoother transition to solid food in the post-weaning period by stimulating feed intake and influencing gut colonization and morphology. So there's a gradual shift up to 22 weeks of age, with Bacillota increasing while Bacteroidata decreases, and that stabilizes at 22 weeks of age. Fermentable fiber in post-weaning feed stimulate gut fermentation and promote proportion of fiber-degrading Bacteroidota, while oligosaccharides utilizers Bacteroides decrease. 59.6% of the fiber-degrading bacteria belong to the phylum Bacteroidota. These microbial shifts are primarily driven by dietary changes, as weaner feeds typically include grains and pulses that provide a high level of starch, protein, and fiber. Now, there was a study done that looked at pigs that were 54.7 kilos plus minus 4.1, and they randomly assigned these, there were many sows, these sows to 4 diets. 2 of the 4 diets contain low digestible cornfield peas meal as a protein source, whereas 2 of them comprised of high digestible corn soybean meal as a protein source. They fed them for 3 weeks and, for 9 weeks, and included a 19-day adaptation to the diet, and then they euthanized one pig per diet. And they looked at the whole gastrointestinal tract. Now, I'm only going to talk about the digester, which is the bottom row of this pig. The major phylum identified based on the bacterial proteins, so you looked at the proteins of the bacteria, in the digester along the gastrointestinal tract were Bacillota, followed by Bacteroidota and Actinomycetota. Alpha diversity was highest in the cecum and colon, and that's probably because the small intestine is challenging for fermenting bacteria due to the pH conditions, the high oxygen level, and fast digester passage. The relative abundance of bacteria, so this is the table they said. The relative abundance bacterial families identified based on the peptide sequence in the digester samples along the gastrointestinal tract section is shown in this table. Proteins belonging to the Bacillota showed higher peptin counts in the small intestine compared to the cecum and the colon. This trend was also shown based on operational taxonomic taxonomic units counts in young pigs, whereas this was the opposite, was described in the literature in 28-day-old piglets. Proteins of the lactobacilliaceae, and this can be seen when you look in the left-hand side, the highlighted bacteria species. Lactobacilliaceae, Clostridiaceae, and Veillonella-Lalaceae dominated the bacillota in all sections. So it went throughout the small and the large intestine. Lactobacilliae proteins were considered high in the small intestine compared to the large intestine. Proteins of the Bacteroidota were highly abundant, where its average occurrence was much higher in the large intestine compared to the small intestine. Let's have a little talk about other actinomycetota bacteria, the Bifidobacteria Terriaceae. They're providing acids from a wide range of carbohydrates via a specific metallic pathway called the bifid chant. Feeding dietary fibers leads to a lower pH of the gut content, and that causes an environment which is favorable for bifidobacterium. In several studies, high fiber diets cause an increase in beneficial bacteria such as the Bifidobacteriaceae in the cecum and support the intestinal epithelial morphology. Both contribute to pig's gastrointestinal health and lead to a higher defensive power against harmful bacteria. So let's have a look at the bacterial metabolites, the end products, which play an indispensable role in regulating energy, homeostasis, and other physiological purposes and influence the activity of the digestive enzyme. Moreover, microbial metabolites can communicate with the gastrointestinal mucous system to influence intestinal homeostasis and neurological disorders. So, what are these gut microbiome products? So we have the short-chain fatty acid, the branched-chain fatty acid, secondary bile acids, polyamines, inoles and phenolic compounds, neurotransmitter, their precursor, and vitamins. We also have other ones. So in the Bacillota family, we also have the lactate, which comes from Lactobacilliaceae. We have in the Clostridiaceae, we have the hydrogen sulfide. In the Enterobacteriaceae, the Pseudomonadota. We have ethanol, we have bacteriocins, and especially E. coli creates an anaerobic environment by scavenging oxygen. Now, short chain, I'm just going to highlight a few of them here. Short chain fatty acids, they stimulate cell proliferation, suppress pro-inflammatory cytokines, upregulation of tight junction proteins, act as precursor for neurotransmitters. The branched-chain fatty acids suppress pro-inflammatory cytokines, impair gut barrier function, upregulate pro-inflammatory cytokines. Lactate reduces the pH, thus preventing the growth of potentially pathogenic bacteria. Bile salts regulate glucose and energy homeostasis, suppress pro-inflammatory cytokines, and impair oxidative stress coping mechanisms. Polyamines, and now this has become where it becomes a little bit, we really need to have a balance. Improve fetal development, suppress pro-inflammatory cytokine, enhance oxidative stress, alleviate diarrhea, may cause damage to the intestinal morphology. So you obviously can't have too much. Phenolic and phenolic compounds, they attenuate oxidative stress. However, they induce leaky gut and reduce growth performance. ammonia, which are also produced by some of the bacteria, inhibit mitochondrial respiration, inhibit short-chain fatty acid oxidation. And we have the hydrogen sulfide, acts as a signaling molecule, inhibits cytochrome oxidase activity, hinders cell proliferation, and induces intestinal inflammation. Then we have the neurotransmitters. They ameliorate tail biting, apparently. So vitamins, obviously vitamins are something good. They serve as a coenzyme in neurological processes. They're essential vitamins for proper blood clotting. So there's evidence that dietary intervention can modulate the gut microbiome and its metabolites and improve health and performance in pigs. Optimizing feed and feed supplements has also resulted in an increased survival rates of weaning piglets. Additional supplements to early feed, such as fermented and excreted wheat bran, probiotics, prebiotics, and amino acids show positive improvement in gut microbial profiling and morphology. A high crude protein level in post-weaning feeds can contribute to diarrhea due to the undigested protein fostering pathogenic bacteria in the gut, such as Enterobacteria family, which are the E. coli. Diets high in pectin and fish protein may reduce lactobacillus, increasing susceptible to pathogens, while plant-based proteins help to lower E. coli counts, albeit with some impact on the growth. We did a fermentation study and we looked at ingredients: barley, maize, wheat, canola, soybean meal, and lupin at large 1.18 millimeter and small 0.1 to 1 millimeter particle size. We also looked at enzymes, but I'm concentrating here on the other one, the particle size especially. So large particle cereals retain threefold more starch post digestion than small particle cereals and protein. Large cereals stimulated starch fermentation and increased short-chain fatty acid, with the dominance in zucchini vibrio, a starch-degrading genus, reducing the microbial diversity, while small cereals and protein source favored insoluble fiber fermentation in this in vitro gut fermentation. Hemicellulose degrading genera such as Fibriobacter, Bovitella 9, and Bacteroides were prevalent in small particle cereals and protein sources. So this really means that particle size impact on gut fermentation highlights the need to consider particle size in pigments diet formulation to promote healthy gut microbiota. And I encourage you to have a look at Lenny's poster. He will deal with this in more detail. So in summary, formulation of post-weaning feed should be carefully examined to provide adequate nutrition but also maintain the healthy gut microbial profile. And that's where I'm stopping. Thank you for the wonderful, and I thank my wonderful team for pushing this microbiome research. Thank you for having me.